This course on electrochemistry will give an overview of the electrochemical behaviour of species in solution. The first question, of course, is why are we interested in electrochemistry? Well, chemistry is all about electrons, and electrons are the foundation of electricity, and we're interested in what happens when an electron goes from one place to another. The example here is when we have sodium and chlorine reacting together, the electron hops from the sodium to the chlorine and forms these ion pairs. Okay, and this is what forms salts. So we are interested in what happens when this electron goes from one place to another. So fundamentally, this movement of charge results in ions. So we need to understand a little bit about how ions behave and what is it that controls whether or not a reaction can happen under these conditions. Fundamentally, through better understanding of these electrochemical processes, we will understand better about how chemical reactions happen and how electrostatics are important. Electrochemistry is used widely from looking at energy storage and managing reactions through to our electronic devices. Anywhere that we have any level of electricity storage, we have chemistry happening. When we think about things like electron transfer, it's not a trivial subject. We will be discussing more of it in years 3 and 4, so please do bear in mind that this is a little bit more complex than it might initially seem, but through our better understanding of the electrochemical processes in cells, we'll gain a better understanding of the chemistry that we're studying. To give a quick overview of this session, we're going to be looking at the fundamentals of electrochemistry. So what is it we need to consider when we think about electrochemical processes? We'll look into ions and ion behaviour and how they behave in solution. We'll then be looking at how they diffuse and migrate through that solution. We'll then consider the concepts around electrochemical equilibrium and in particular the thermodynamics that happen in electrochemical cells. And finally, we will be looking at electrode processes. So thinking about how do the kinetics of an electrochemical process affect the rates of our reactions. We'll need to quickly reintroduce you to some areas that you have covered in first year. This won't take very long, but it's important that you are familiar and understand what this terminology that we'll be using it means. So whether we're thinking of electrode potentials, whether we're thinking standard electrodes, cell potentials, cations, anions, cathodes, anodes. So we need to do a very quick recap of this material. Electrode potential is a first-year topic which you may well have come across as half-cell potentials, reduction potentials, or indeed half-reactions. These will be fairly familiar to you, so you'll have seen things that look a bit like this, where we have copper 2+ being reduced via the addition of electrons to copper metal with an associated cell potential. Another way of representing such an equilibrium is using this bar here. So here we have zinc 2+ being reduced to zinc metal. And here we have a different cell potential value. There's a range of nomenclature that's used in this, but by convention, all of these cells are written as reductions. This is simply a convention. So X plus an electron going to X solid or X gas. All of these are measured under standard conditions. So remember that our standard conditions here are the pressure at 1 atmosphere and our concentration, M, which is molality. This is looking at moles per kilogram of solvent, are measured at 1 mole per kilogram. And the reasons for this will become apparent to you as we go through. Fundamentally, an electrode potential cannot be measured in isolation. We need to measure it relative to something else. So this brings us on to the topic of standard electrodes. As mentioned, they can't be measured directly. This is akin to the sound of one hand clapping. We cannot look at one thing on its own. It has to be measured in reference to something else. So the concept of standard electrodes is important to recognise as well. The standard electrode that we often think of is the standard hydrogen electrode. So what we do is we set up a reaction where we pass hydrogen at 1 atmosphere over a platinum electrode, and this is in a 1 mole per kilogram of hydrochloric acid. This is defined as being zero potential. Okay, so however we choose to write this, whether it's H plus going to H2 or H plus going to H2 over a platinum electrode, the potential is the same. We define this as zero, and everything else is measured relative to this. It's a definition, it's not an absolute. It is impossible to measure a potential directly of a single electrode. So it has to be measured relative to that something else, and we define the hydrogen electrode at zero, so that everything else is measured relative to it. So when we have our zinc potential from the previous slide, that is measured relative to the hydrogen electrode. The cell potential itself is worth revisiting, and if you remember, this is the result of combining two half cells. So if we have our copper and zinc cells here, we're going to combine them together. And remember, they're both written as reductions, so what we need to do is we can't add them together, we need to subtract them, because remember, we have to eliminate the electron term. So we subtract one half cell from the other. So if in doubt, we look to get rid of the electron term. So we balance the charges. Here we're fortunate because we have 2 electrons in each. Things can be subtracted directly from each other. And we subtract the cell potentials. And then finally we rearrange the equation so that it all makes sense. So here we have copper minus zinc, going to copper solid minus zinc solid. Add zinc to both sides, subtract zinc ions from both sides, and we end up seeing that if we have copper in solution with zinc solid, we will get copper solid and zinc in solution. And we can see that the cell potential, we simply subtract minus 0.76 from 0.34, and we end up with our overall cell potential. This gives us an indicator of the direction of thermodynamic outcome for a reaction such as this. With regard to the thermodynamics of cell processes, we can use these cell potentials to predict the thermodynamics of reactions. Where we use delta G standard is minus NFE standard, where N is the number of electrons in the reaction and F is the Faraday constant. So this can be used to predict a wide range of reaction outcomes, not just those happening in electrochemical cells, because electrochemistry happens all over. Anywhere you have an exchange of electrons, we have electrochemistry. But this only predicts the thermodynamics, and we have to consider the kinetics of a reaction as well. And this study of electrochemistry allows us to look at the ionic behavior in solutions, the effect of concentrations and in particular solution activities, and what happens when reactants start moving through solution, this diffusion happening. We now need to consider the ions and the electrodes. So just to clarify definitions, a cation is attracted to the cathode, an anion is attracted to the anode. Worth remembering, it is simple terminology. A cation is positively charged, so that means it's attracted to the cathode, which means the cathode must carry a negative charge. These are the source of electrons for cations, so a cation will migrate to the cathode, pick up an electron, and then diffuse back into solution as the reduced form. Anions are negatively charged and are attracted to the anode, which means the anode must be positively charged. And it's the anode which collects the negative charge from the anion, then the oxidized species diffuses from the anode. So it's simple terminology, but it's important to remember which way round we're considering it. We now need to think of ion-ion interactions in solution. So when we think of ionic interactions, recall from first year that they are governed by Coulombic forces. And they're derived from this Coulombic potential V of R, which when we sketch it, looks a bit like this. This is just a simple potential showing how the potential varies. Q1 and Q2 represents the charge on each of the ions, while R is the separation between them. And remember again from your intermolecular forces that force is the first derivative of potential with respect to R, so we find our first derivative here, and we get a graph that looks like this. Okay, so the closer the ions are, or closer oppositely charged ions are, the more they attract. It's particularly important to pay attention to the signs, the negative here versus no negative here. Make sure that you can achieve this result. So make sure that you can do a first derivative of this expression with respect to R and come up with this final answer. If it helps, this 1 over 4 pi epsilon naught epsilon R is simply a constant, and you only need to worry about this section. Okay, so just make sure you can reproduce that. Ions in solution can readily form ion pairs. So no great surprise that opposite charges can be held together. So a positive is held to a negative charge. This effect is strongest for these small, highly charged ions, so magnesium 2+ is a key example. But we have to also consider the dielectric properties of the constant, that epsilon R component, the relative permittivity. We'll talk more about this later on, but this relative permittivity is key in whether or not ion pairs will form. If we have a higher relative permittivity, that means electric fields can readily permeate the solution, we have lower ion pair attraction because it can feel more of the other ions in solution and therefore disperses more throughout solution. Whereas if we have a lower relative permittivity, it cannot sense other ions, so an ion pair will tend to form under these conditions. With this Coulombic force, it's important to remember I've represented it here as Q1, Q2, but you will also see Z used to represent charges in equations. This appears all over in textbooks. You'll sometimes see it as Q, other times you'll see it as Z, but you do need to be familiar with either representation. The next concept we wish to introduce is that of the ionic atmosphere. So when we look at a solution of ions, they'll be dispersed throughout solution, they'll be in constant movement. Very few ions are actually held in ion pairs in aqueous solution. Most of them are solvated, so most of these ions will have water molecules around them in aqueous solution. But for any given area in this space, any one ion will be surrounded by a very slight excess of counterions. So if we take this one in the center, this positive charge, If we look at this cation and we draw a circle around it, we can see that there is a slight excess of the counterions. This is something we call the ionic atmosphere. The ionic atmosphere is simply a result of thermal motion which distributes material equally throughout the solution, but also considering the Coulombic interactions. So like charges will repel while opposite charges will attract. And this means that around any one ion there will be an ionic atmosphere with a very small but opposite charge around it. It's something that is dynamic in nature. These are in constant motion. These things are constantly moving through the solution. There are a number of different ways of considering the ionic atmosphere. There are two main ways that I'm going to cover, but neither is more or less valid than any other, but they have the same general features. So when we think of an ionic atmosphere, if we define a volume in our solution, this particular volume will have zero charge. So I'm just going to draw a circle to define an area in this particular solution. It will consist of a central ion of a given charge and a surrounding atmosphere of equal and opposite charge. So inside the sphere, the whole thing has zero charge, but it's centered on a positive charge here, which means the ionic atmosphere has a net negative charge to compensate. When we start to change the concentration of our solution, the ionic atmosphere changes as well. So at lower concentrations, we find that we have to go further to find an ionic atmosphere of equal and opposite charge. So if we have a high concentration, we end up with a smaller ionic atmosphere because we don't have to go as far to find an equal and opposite charge, whereas at low concentrations we have to extend the boundary a long way out to capture an atmosphere of equal and opposite charge. The ionic atmosphere serves to stabilize this central ion. Fundamentally, a free ion is unstable, but if we can surround it by an equal and opposite charge, we offer a degree of stability. However, the fact that it is an equal and opposite charge around it means it is held loosely around that ion and fundamentally affects its motion. If the charge moves, then an atmosphere has to move with it. Another concept to cover is the idea of solvation shells. So whenever we have an ion in solution, the presence of solvent dipoles affects the solvation of these ions. We normally consider water as a solvent, which is a very highly polar medium, but the dipoles of water align differently around cations and anions. If we take a cation, for example, the delta minus that's present on the oxygen atom in water will preferentially align with the cation, while an anion, we will tend to see the delta positives aligning with the anion. So we get a slightly different orientation. The overall alignment will vary with distance from the central ion and how big this central ion is. At different levels, different distances from this, the degree of alignment will vary. So the next shell out won't be quite so well aligned, and we get to a point where we just have free water in solution, which isn't affected by any of the solvation shells. So these solvent molecules here are locked and held in a solvation shell, and they will move with the charge. They're not free in solution, they are tied to the charge, they will move with that ion. So these solvation shells also affect the ion mobility. The next thing to consider is this dielectric constant carrying the symbol epsilon. It's often seen as a measure of solvent polarity, but it's fundamentally a bulk property of the solvent. It represents the ability for a solvent to carry an electric field. So whenever we think of charges, we have electric field lines which by convention go from positive to negative. If we have a high relative permittivity, that means the solvent has a high ability to transmit that electric field, which facilitates long-range ion-ion interactions. If, however, we have a very low relative permittivity, then there is very little transmission and the field is not able to permeate. So we only end up with short-range ion-ion interactions. What this means is for a low epsilon, we will tend to form ion pairs because as soon as one charge encounters another, they'll stick together. There's nothing else to stabilize them. Whereas in a high relative permittivity environment, these ions can detect each other from a long range and they offer long-range stabilization. So it's important to remember this dielectric constant and the role it plays in forming ion-ion pairs. So just to summarize the primary concepts that we've discussed here, ionic interactions are governed by Coulomb's law, they're predictable and they're well defined. And under ionic interactions in water, direct ion-ion pairing is very infrequent. We need to consider the importance of ionic solvation. So when we're thinking about an ionic atmosphere where we have an equal and opposite charge around in this ionic atmosphere, we also have solvent molecules tied up in solvation shells around it, and both of these affect ionic mobility. They affect the ability for it to feel the electric field outside the atmosphere, and the mass that we move with the solvation shells is increased, which also affects the mobility. And finally, the dielectric constant, which affects the ratio of the direct ion-ion pairing to ion solvation. In the context of this course, we'll only be considering aqueous environments. However, we can do electrochemistry anywhere that we have a solution. So other solvents can be considered as well. So it's worth bearing in mind the effect that all of these have.